Hello, everyone. Today, I am very pleased to introduce our work toward real-world infrared image super resolution, a unified autoregressive framework and benchmark dataset. This work focuses on real-world infrared image super resolution, which aims to recover high-resolution and high-quality infrared images from low-resolution infrared observations. Infrared image super resolution is important for many perception tasks, such as object detection, target tracking, and autonomous driving, especially under low light or adverse conditions. However, real-world infrared SR is not simply visible image SR applied to another spectrum. There are three main challenges. First, most existing IISR methods rely on synthetic degradations. The LR images are usually generated by downsampling or artificial blur, which cannot fully reflect real infrared camera optics and sensing noise. Second, real infrared images suffer from infrared-specific degradations, such as defocus blur, motion blur, sensor noise, and radiometric drift. These degradations are often coupled together and spatially non-uniform. Third, infrared images have a thermal structure mismatch. The high-temperature regions do not always align with object boundaries. As a result, existing methods may overfit thermal peaks while producing blurred contours or thermal drift. Therefore, real-world IISR requires not only a real benchmark dataset, but also an infrared-aware super-resolution framework. This motivates our proposed FLIR-IISR dataset and real IISR method. Our work makes three main contributions. First, we construct FLIR-IISR, a real-world benchmark dataset for infrared image super resolution. It contains 1,457 real paired LR-HR infrared images, captured across 6 cities, 3 seasons, and different real blur patterns. This dataset provides a more realistic benchmark for evaluating IISR methods under real imaging degradations. Second, we propose Real IISR, a unified autoregressive framework for real-world infrared SR. Different from directly applying visible light SR models to infrared images, our framework introduces thermal structural guidance and a condition-adaptive codebook so that the model can better handle infrared-specific degradations and reconstruct sharper structures. Third, we introduce a thermal order consistency loss. Instead of only matching absolute pixel values, this loss preserves the relative thermal intensity ordering between the super-resolved image and the high-resolution image. This helps reduce thermal drift and maintain more physically consistent infrared reconstruction, especially under slight misalignment. Overall, our work provides both a new benchmark dataset and an infrared-aware super-resolution framework for real-world ISR. Given a low-resolution infrared image, our goal is to reconstruct a high-resolution image with both clear structures and reliable thermal distributions. To achieve this, we build a unified autoregressive framework based on a VAR backbone. First, we introduce the Thermal Structural Guidance module. Since thermal radiation regions may not perfectly align with object boundaries, we extract both heat cues and edge cues from the LR image. These two types of information are fused and then injected into the image features through cross-attention. In this way, the model can better align thermal responses with structural boundaries. Second, the guided features are sent into the VAR backbone, which performs scale-by-scale next-scale prediction. Instead of generating the whole image at once, the model progressively reconstructs the image from coarse to fine scales, which helps preserve global structure and recover fine-grained details. Third, we propose a condition-adaptive codebook. In standard VQ-based generation, each discrete token corresponds to a fixed code embedding. However, real infrared images contain different degradations, such as blur and noise. Therefore, we adaptively modulate the codebook embeddings using degradation-aware priors, allowing the same token to produce more suitable features under different degradation conditions. Finally, we introduce the thermal order consistency loss. This loss preserves the relative thermal intensity order between the SR and HR images, which helps reduce thermal drift and maintain physically consistent infrared reconstruction. Overall, the VAR backbone provides the autoregressive generation ability, while infrared-specific priors guide both token generation and codebook decoding. We construct FLIR-IISR, a real-world IISR dataset that contains 1,457 paired L-R-HR images captured across 6 cities, 3 seasons, and 2 real blur patterns of optical and motion blur across 12 scene categories stored in lossless BMP format to preserve radiometric fidelity. LR and HR pairs may exhibit slight subpixel misalignment due to the defocus-refocus acquisition process. As shown in the figure, an automated capture program was developed to generate paired LR-HR data. Upon each electronic shutter trigger, the camera first performs automatic focusing to acquire a sharp HR image. Then the program randomly adjusts the electronic focus ring to produce multiple defocus levels. One blurred frame is randomly selected and downsampled by 4 times to obtain the LR counterpart. This process ensures consistent viewpoints while providing realistic degradations, including defocus and motion blur, caused by moving objects. This is the no-reference metrics comparison on FLIR-ISR and M3FD datasets. This is the reference-based metrics comparison, as well as the efficiency analysis and ablations. Thanks for listening.